Very excited to be here today. I'm just giving sort of a short talk on system-wide monitoring for anomaly detection. This is largely based on some of the last work of my PhD, and so I'm sort of excited to be sharing that with you today. And the talk that I'll be giving today relies on the fact that a complex system can largely fail in two ways. So the first way is that the failure could be local to a specific subsystem. And a great example of this is the way that deep neural networks and other opaque learning systems fail. In fact, we've seen many adversarial examples. So you have a deep neural net that's trying to classify images. It sees this image of a pig and classifies it as a pig, but with a little bit of noise, automatically it fails, and then it classifies this image as an airliner. And while these are sort of fun to look in isolation, when these are fed into bigger systems like autonomous vehicles that are doing safety critical and mission critical things, these can have large failures. And that sort of leads to what happens in the second type of failure, where you have a failed cooperation amongst subsystems. And the self-driving car is a very good example of this because it has a lot of different modalities. And it doesn't always know how to process that, and the parts don't really know how to communicate together. And we see this type of behavior at two sides of the spectrum. So there's been the GM's ultra cautious self-driving car with this type of herky-jerky behavior, where because it doesn't know how to deal with the LiDAR versus the vision system data, it actually chooses to start and stop for anything that it perceives in its way, instead of just stopping for things that could be threatening objects. Now, at the other side of the spectrum, we have systems that are very comfortable for people, but they're not that safe. And this is what happened in the Uber self-driving car accident, where basically there was different information coming from the LiDAR and the vision system, and the system didn't know which system or which subsystem to trust in that scenario. And so for those of you that are sort of familiar with my thesis work, this has been the long-running example that I've evaluated my system on. And so hopefully it plays. Is it playing? I can't see it on my screen. Sorry. There. Is it going? Oh, I think so. Maybe. Anyway, I'll just describe it. So what happened in the Uber self-driving car accident, I'm not sure if it's playing, is that there was a pedestrian crossing the street with a bicycle, and the vision system perceived that as a bunch of different labels. So it said that it was an unknown object, and then it said that it was a vehicle, and it didn't know which label to trust, and so it actually discounted that entire system and said not to trust it, and that object that it detected was not there. Even though the LiDAR system, so the system that's producing these large point cloud data sets, actually detected the person with enough time to stop. And this is a really unfortunate case of what happens when you have systems that don't know how to process multiple modalities, and specifically, you don't have a system-wide monitoring architecture that can deal with these types of failure situations. And so what I built was a system-wide monitoring architecture that can largely reason in 3 steps. And so I'm going to be talking about the third part. I'll be talking about the explanation synthesizer for this short talk today, but I'm happy to talk about the other parts of this architecture as well offline. And so the way that this works is largely you generate qualitative symbolic descriptions for each committee. An example of a committee is a group that's working towards a common goal. That's something like the braking, the steering, and the power control that's reporting to the tactics committee. They're all sort of working on the same thing. And then from there, you look at those qualitative descriptions and input that into a reasonableness monitor, which gives you a justification and an explanation of why it believes that those descriptions are reasonable or not. And this builds upon previous work that I showed in ACS along with Jamie Macbeth and Evelyn Florentine on building these types of monitoring systems for opaque scene understanders. I've applied that to full system design. And now the third part, which I'll be describing in detail, is how I use a synthesizer that can reconcile these inconsistencies between monitoring outputs. And that's exactly what happened in the Uber self-driving car accident, where it wasn't able to process the inconsistency between the vision and the LiDAR system. So the way that the synthesizer works, and I'll be going through the Uber self-driving car accident, is basically it takes in the explanations from the reasonableness monitor. So it takes in several different explanations. The first explanation that we got from the vision system says here that the vision perception is unreasonable because there's no common sense data supporting the similarity between a vehicle, a bike, and an unknown object, except that they can be located at the same location. And it actually indicates that the component's output should be discounted. Now I'm showing this in natural language for a case of demonstration, but these are also, these are actually processed in symbolic triples, which I'll show on the next slide. The LiDAR system's explanation basically says that the LiDAR perception is reasonable. An object that's moving of this size is a large moving object that should be avoided. So it has a sensor interpreter that's able to give a higher level concept to what it's perceiving. And then finally, it says that the system state is reasonable given that the vehicle has been moving quickly and proceeding straight for the last 10-second history. Now, using those three explanations, the synthesizer is able to say, what is the most reasonable thing that you should do in this situation? So it actually says here that the best option is to veer and slow down. Because the vehicle is traveling quickly, it knows that it's traveling too fast to suddenly stop. It knows that the vision system is inconsistent, but the LiDAR system has provided a reasonable and strong claim to avoid the object moving across the street. Now, the way that this is actually processed, again, is through these symbolic reasons. This is just a small subset of what you see. And you can see the parts here that I highlighted that are important to this final explanation. In fact, you can see where it gets the information from the system state here in red, where it gets it from the vision in yellow, and where it gets the information from the LiDAR in blue. So how does the synthesizer actually decide and figure out what things to prioritize in these sorts of situations? Well, the explanation synthesizer is meant to deal with these types of inconsistencies. And the way it does that is it builds an argument tree. And in theory, this could be queried for support and counterfactuals. I haven't gotten the chance to explore that much in my thesis work, but that was sort of the idea of this reasoning process. But it also needs to take in a priority hierarchy so it knows what things to value in different cases and when it needs to intervene. And it represents that as basically an abstract goal tree. Now, for the self-driving car example that I showed, the priorities are basically passenger safety. That also encapsulates pedestrian safety close to the vehicle. That's part of it. And it goes down to passenger perceived safety, comfort, and finally efficiency. Since this is a short talk, I'm just going to be talking about passenger safety, how I represent that, and how I use that. And basically, I say that a passenger is safe if the vehicle is traveling smoothly, so it's proceeding at the same speed and direction, and it avoids threatening objects that could be in its way. Now, the way that that's done is largely through first order logic. So I basically define that as a passenger being safe if the vehicle at two successive states, S and T, are traveling at the same qualitative velocity, and there are no objects at either of those states that could be a threat. Then I say that the passenger has the property that it's safe, and I represent that as this abstract goal tree. Again, that the passenger is safe if it goes through safe transitions. That's what's underlined here in green. And it doesn't encounter any threatening objects. That's highlighted here in blue. Now, I said that this builds a sort of argument tree, so I just wanted to give a little preview of what that looks like for this example. So again, this is represented as a set of rules, and basically I backwards chain that to get to the goal that I want to get to for the passenger to be safe, which builds an and/or tree that looks something like this. And again, in this scenario, because we're looking at self-driving, a threat, there are many different threats that you can encounter, but the threat in this case is that it's defined as a large moving object that's somewhere close to the vehicle. And so when you go through the scenario and use this abstract goal tree, what you find is that the not threatening objects has actually been violated by the LiDAR. So the LiDAR actually produced a strong and reasonable claim that there's a large moving object that could be classified as a threat, and that's something that should be avoided. What's important to note here is that it's not saying necessarily that the vision system is wrong just because it's oscillating between a bunch of labels. It's just saying that the explanation that's coming from the LiDAR system is a lot stronger, and it's something that's critical in this sort of decision making. And again, that's sort of what leads to this final explanation here. Now, one of the difficulties in looking at errors and things that are critical, like self-driving, is we just don't have the data to validate these types of approaches. And so one type of evaluation we did was in simulation. And for people that are interested in thinking about other types of challenging scenarios, I'm working with some colleagues here on thinking about these challenge scenarios for anticipatory thinking. And so what you see here in this simulation is that moments before the vehicle swerves out of the way, it actually finds that there's something anomalous happening, that the vision system's inconsistent, and the LiDAR system has actually detected a large moving object that should be avoided. And it goes and it takes a different route here. And so I've done this with several different scenarios. This is sort of the champion one for my thesis. And so just in summary, this is one way that I've been thinking about reconciling these types of errors, especially in complex systems. And I'm also inspired by a lot of the crash scenarios that are being that have been proposed to look at these sorts of difficulties, especially in self-driving cars. But some ongoing work. So I am finishing my dissertation, but I continue to sort of think about these problems. I've looked at vehicle logs after the fact. So we've generated several logs from scenarios and been able to detect failures using this approach. I've also added my own errors. So one of the difficulties with self-driving is that all the data sets are very reasonable. So I scrambled different labels and added my own errors on these data sets, and we're able to detect them using this approach. I'm also interested in looking at other people's methods and seeing if I can detect these types of failures and errors. Fortunately, most of them are not open source. And finally, something that I'm interested in discussing offline is thinking about other applications for this, especially in negotiation and argumentation. So I know I think I'm out of time. I'm happy to take a question and talk offline.
Great. Well, Matt has a question for you. He asked, is the priority hierarchy grouped in a way that no matter how much a lower priority is violated, will it ever trade off a higher priority?
That's a great question. So the higher priorities have to be satisfied. If they're not satisfied, it's always going to intervene. And it's actually very rare that it gets down to the lower priorities. I've only seen that in sort of very scenic driving scenarios where you might take a wrong turn. But the first priorities are always met first before moving down to the later ones.
Okay. Thank you.
Great.